Hello, welcome to today's lesson on power in the context of electric circuits. Today, we will start by recapping previous learnings about power and energy transfer. Next, we will derive the power equation for circuits. Finally, we'll apply the power equations to various scenarios. In the previous lesson, you have learned how to calculate energy transferred in the context of electrical circuits. Today, we will combine this with your understanding of power from the energy unit to explore power in the context of circuits. We know from our previous unit on energy that power P is defined as the energy transferred, E per unit time, T. Mathematically, this is written as P equals E divided by T. We also know from our last lesson that, in the context of electrical circuits, energy transferred, E, can be represented as the product of charge, Q, and voltage, V, or E equals QV. We can substitute E equals QV into the power equation P equals E divided by T to get a new equation for power in the context of electric circuits. This can be written P equals QV divided by T. We also know that current I is the rate of flow of charge, or mathematically, I equals Q divided by T. Therefore, we can substitute Q over T with I in our equation for power. This gives us P equals Q over TT times V, which equals IV. This equation, P equals IV, is a fundamental relationship because it links power, current, and voltage in a circuit. It helps us calculate how much electrical energy is being used or generated by a component, which is essential for designing circuits and understanding how electrical devices operate efficiently. Sometimes, however, we may not be provided with one of the current or the voltage. Hence, we can use Ohm's law to derive alternative forms of this equation. Remember that Ohm's law states that V equals IR, where V is the voltage, I is the current, and R is the resistance. For example, suppose we have a component where we know its resistance and the current flowing through it, but do not know the voltage across it, and we want to calculate its power. We can substitute V equals IR into the power equation P equals IV to get P equals I times IR, which simplifies to P equals I squared times R. We can directly plug the current and the resistance into this equation to calculate the power. Now suppose instead that we know the resistance and voltage but do not know the current. Again, we can use Ohm's law. Ohm's law can be rearranged to give I equals V over R. Substituting this into P equals IV gives P equals V over R times V, or P equals V squared over R. Depending on what is given in a problem, you can choose which of these equations to solve for the power. To better understand the use of these equations, let's go through a worked example. Imagine we have a toaster connected to a mains supply with a current of 2.5 amps passing through. First, we need to identify the given values. The current drawn by the toaster, I equals 2.5 amps. The voltage of the supply V equals 230 volts, the UK mains voltage. The next thing we need to do is choose the relevant formula. From the values given, we can see that we have current, I, and voltage, V. Therefore, the relevant formula to use is P equals IV. Lastly, we need to calculate the power. Plug the given values into the formula to get P equals 2.5 amps times 230 volts equals 575 watts. Hence, the toaster has a power of 575 watts. Let's tackle some more problems to further consolidate our knowledge. How can we calculate the power dissipated by a 10 ohm resistor when a current of 2 amps flows through it? Firstly, we need to identify the known values. The current, I equals 2 amps, and the resistance, R, is 10 ohms. Next, we need to choose the relevant formula. From the values given, we can see that we have current, I, and resistance, R. Therefore, the relevant formula to use is P equals I squared times R. Finally, we need to substitute the known values. When we do this, we get that P equals 2 squared times 10. When we calculate this, we get that P equals 40 watts. So, the power consumed by the resistor is 40 watts. Let's try another problem. What if we want to determine the power dissipated when the voltage across a 5 ohm resistor is 20 volts? Firstly, we need to identify the known values. The voltage V is 20 volts and the resistance R equals 5 ohms. Next, we need to choose the relevant formula. From the values given, we can see that we have voltage, V, and resistance, R. Therefore, the relevant formula to use is P equals V squared divided by R. Next, we need to substitute in the known values. This gives us P equals 20 squared over 5. Finally, we need to calculate this to see that P equals 80 watts. Thus, the power dissipated by the resistor is 80 watts. Let's try one more question. Suppose a heater has a power rating of 2 kilowatts when connected to a 250 volt supply. What is the current flowing through the heater? Firstly, we need to identify the known values. The power P equals 2000 watts and the voltage V is 250 volts. From the values given, we can see that we have voltage, V, and power P, and we want to calculate the current I. Therefore, the relevant formula to use is P equals IV. Next, we need to rearrange the formula to solve for current. This gives us I equals P over V. Let's substitute the known values. This gives us I equals 2000 divided by 250, which gives us 8 amps. Hence, the current flowing through the heater is 8 amps. In today's lesson, we explored the concept of power in electrical circuits and learned how to calculate it using different equations. We began by understanding the basic equation for power, P equals IV, which connects power, current, and voltage. This equation is crucial for determining how much energy is being transferred in a circuit. We also discussed alternative forms of the power equation, such as P equals Y squared R and P equals V squared over R, which can be used depending on the given values. These variations help in solving different types of problems effectively. Through practical examples, we applied these equations to real-world scenarios, such as calculating the power consumed by a resistor or determining the current required by an appliance. Understanding these relationships helps in analyzing and designing circuits that function efficiently and safely.